Um, First of all, I want to clarify, Carly and I are sharing a room, which is why my microphone is off. Don't worry, it's not some magic that I've learned. Um, and yeah, so welcome, first of all, to our first ever microplastics webinar. We're so excited to have you here. And the Nordic Water team has been planning this for a long time, and we have our wonderful microplastics expert, Dr. Roxana Sühring, joining us from TMU today. So a big thank you to Roxana for joining us. So this session will, first I'm going to walk you through NORDIK Institute and a bit of what we do. Then Carly will walk us through some of the basics of what microplastics are. Some of us might not be as familiar with them. And then we'll give it away to our keynote speaker, Roxana, to bring us home with some details about her research. So let's get into it. So before we begin, I'd like to ask you all to reflect on the lens that we are joining from today. So NORDIK Institute works side by side with many Indigenous peoples on the homelands of the Batchewana First Nation, Garden River First Nation, Nissenabe Cree First Nation, and various Métis peoples. We recognize the site on which our office is located as the site of the former Shingwak Indian Residential School. NORDIK Institute recognizes the intergenerational impacts and trauma that resulted, and we commit to honoring this history for the survivors, their families, and for those who did not return home. We actionably commit to building vibrant, strong, continued relations with the local nations of Bawate. In the spirit of peace and friendship, we value our treaty relationship, the lands and waters on which we rely, and Indigenous communities everywhere, while challenging ongoing systems of oppression. All right, so for those of you who might be new to NORDIK, I'll briefly introduce you to our work. So we stand for the Northern Ontario Research, Development, Ideas and Knowledge Institute. That's our acronym. So we're a community-based research hub affiliated with Algoma University, dedicated to building healthy, resilient communities. Our office is in Bawating, otherwise known as Sault Ste. Marie, and our mission is to help northern communities innovate, create, and transform to build resilience and capacity to achieve social, cultural, economic, and environmental justice, all while putting our interpersonal and interbeing relationships first, and along with our goal of sustainability. We have a broad range of research projects on the go. This is just one of the projects that we're talking about today. So feel free to reach out. So now I'm going to introduce some of our team. So we're very lucky to have Dr. Elaine Ho-Tassone as our Director of Operations and Project Lead. She's not only the lead for our project on the water team, but also NORDIK Institute's Director of Operations. So she kind of is the glue that binds us together.
She just joined.
Oh, hi Elaine. I believe she just joined us. Feel free, NORDIK staff, to raise your hand when we call your name. Kiki Vitri is our science lead and is the coordinator for our communities in the North Shore of Lake Superior. Ajaz, hi Ajaz, is our St. Mary's River coordinator based here in the Sioux. And Mark is the Lake Huron coordinator based in Thessalon and Huron Shores. Carly is our wonderful environmental educator. She hosts and creates programming such as this to help facilitate reciprocal knowledge sharing with community members and partner groups. Rohil is our road salts researcher joining us over the summer. He's the newest member of our team and he focuses on the effect of road salts leaching into aquatic environments. And there's me. I'm the summer environmental technician. This is my last day with NORDIK in the office. So thank you so much for having me. And yeah, I focus on community outreach and building relationships with partners. So before we get into microplastics, what is this project we keep talking about? So the Community Water Monitoring Project aims to engage citizens in community-based science, or CBS, related to chemicals, nutrients, and other metrics in the lower Lake Superior and northern Lake Huron watersheds. So our objective is really to develop and evaluate a practical approach to CBS for these communities by developing a framework and piloting this approach and really holding ourselves up as an example that, yes, community-based science can work and can be effective to connect citizens, information, and data locally to scientists and decision makers in other echelons of government, organizations, not-for-profits, and community. So we also host a number of activities such as shoreline cleanups and water treatment plant tours to spread awareness of water education. So why do we monitor? Well, our goals are to, one, engage communities in the lower Lake Superior and northern Lake Huron watersheds to collect this data, right? We're creating a strategy specific to the rural and remote areas of Northern Ontario, such as data needs, sampling locations, tools for those who might not be able to have access to the more high-end, expensive equipment, designing monitoring protocols for CBS data collection and offsetting costs, using strategy to develop and pilot a framework to create direct pathways between Northern Ontario and basin-wide decision makers, and share our results and data at public events, conferences, and things like this. So we're very happy to have you. So we are, of course, more than grateful for our partners, collaborators, and funders, some of which I believe are in the room today. Hi, folks. So we have received funding from the Government of Canada, the Government of Ontario, NOHFC, the City of Sault Ste. Marie, NSERC, Algoma University, Swim, Drink, Fish, MyTax, and Eco Canada. So this really began as a pilot project under Elaine in 2021 to fill the need for water quality data in the Great Lakes. This isn't something that has been done very often, which was surprising to me when I first joined. We really began in earnest in 2024 with 18 sites across the city of Sault Ste. Marie. And now in just 1 year, we've expanded to over 40 sites across multiple communities with nearly 1,000 individual data points collected. So we're very grateful, particularly to the Canada Water Agency and the Great Lakes Local Action Fund for providing us support this year, as well as, of course, our many generous in-kind donations and the time that our wonderful volunteers donate to us every week. So with that, that's a little bit about our project. I want to pass it off to Carly to get into the basics of microplastics. Go ahead, Carly.
Hello, everyone. So yeah, thank you for joining us today, and thanks, Isaac, for the great introduction and passing it along. So for many, like myself, who may be in the environmental or the water field, microplastics may be an everyday topic of conversation in the office or in your everyday life. However, for many others, this may be the first time you're really diving into the topic of microplastics. And what microplastics are. So I'll just begin by going through how we identify microplastics, how we categorize microplastics as well. So what are microplastics? So of course, as many of you may know, plastics don't biodegrade over time like paper or cardboard might. Instead, plastics just break down into these smaller pieces, turning into microplastics or eventually nanoplastics. So plastic itself just isn't strong enough to stay in its original shape. And over time, due to weather, transportation, really anything causes it to break down. So in the photo here, we can see microplastics floating with natural debris. And this often happens due to the size of microplastics, and they're not able to be filtered out. So to categorize a microplastic, it has to be a piece of plastic smaller than 5 millimeters and to around approximately 1 micron. Anything below that would be a nanoplastic. So, like I said, ultimately, these plastics are too small to be filtered out. They end up in our natural environment, in the soil, the wind moves them, and they often end up stuck in the water. So we can actually break microplastics down even further into 5 categories. So we'll briefly go through each of these categories. So the first one is fragments. So fragments tend to be smaller pieces of plastic from a larger object. An example of this could be a candy wrapper that's been broken off. If you have a bunch of paper that was wrapped in plastic originally, that wrapping gets broken up into smaller pieces. Anything that was originally a larger plastic item. The second and the most common form of microplastic is fibers. So fibers are plastic strands found on clothing, blankets, or any other fabric. So what happens is oftentimes people pull a string off of their clothes and just let it go. Well, that ends up in our environment. The most common way, though, is through our washing machines. As our clothes are washed, these fibers break off of our clothes and end up filtering out with our wash water. The third is foam. So foam microplastics are most commonly from food containers or coffee cups like Tim Hortons cups, McDonald's cups, styrofoam takeout containers. That's where we most commonly find those guys from. And then we have nurdles. Nurdles are the plastic pellets used in manufacturing. So often they're melted together to make larger pieces of plastic, but unfortunately, they don't all make it to those larger pieces of plastic and are released. And then lastly, we have microbeads. So microbeads are banned in Canada. However, you may see them still in the store. If you're down like a cosmetic aisle, you'll see them in soaps, even in toothpaste. And what they are is simply just little beads of plastic, most commonly used for aesthetic reasons. They make something look nice, and they can sometimes be sold as exfoliants. But really, it's little pieces of plastic. And if you see poly on the label, like it says there, that's how you know there may be plastic in it. An example of microbeads that I often like to share, especially for those with kids or grandkids, nieces and nephews, is microplastics are often found in kids' toys. So here I have a slime. As we know, lots of kids these days really enjoy playing with slime. And this one's called Cosmic Crunch. And if I take it out and show you, there's actually, I don't know how well we can see this, there's actually pieces of microbeads all throughout it. So if I was a child and I was playing with this outside, for example, very unlikely I'd be able to clean it all up. These microbeads would then be in our environment. So just an example of a toy that could be used every day that includes microbeads. Okay. So next, I just want to briefly talk about wastewater treatment plants. So unfortunately, treatment plants are a major concern for microplastics. Research completed by Patagonia estimates that 40% of microfibers, so those pieces of string that we get from our clothes or fabrics, are not filtered at wastewater treatment plants, which of course is a huge problem, especially considering, like I mentioned, a lot of those fibers come from our washing machines. So for example, PUC in Sault Ste. Marie does not filter plastics from wastewater. And the 2 wastewater facilities in the Soo release water back into the St. Mary's River. So any microplastics going through these filters are just going straight back into our water here. So there's no final filtration before water is released, which is a big concern for the St. Mary's, the fish in the St. Mary's, the fishermen at the St. Mary's, and whatnot. So I just wanted to mention that. I want to open the floor and see where everyone thinks these microplastics come from. I mentioned a few ways, like the microfibers, but feel free to drop an answer in the chat and Isaac and I will monitor it. And let us know what you think of where these microplastics come from. And then I'll share a few more ideas as well. So I have a little bit of an interactive section here. Let's see. Yeah, feel free to, or if you're comfortable using your microphone, feel free to shout it out as well. Stormwater, yes, great answer. That is on my list here. Stormwater runoff, construction sites, great answer, Joni. A lot of industrial activities, a lot is released from that.
Something that I didn't realize until I worked here was how much of our clothing is plastic, even if it doesn't say, polyethylene or whatever in the label, it can still contain plastic threads, which can be used to make the stitches. Oh, agricultural practices. That's another great example, Kaylee. Thank you very much. Grocery packaging, that's a big one, of course. A lot of the microplastics come from styrofoam and packaging and that sort of thing as well.
Yeah, so thanks everybody for your answers. Great answers. I also want to mention one that wasn't mentioned yet, which is recreational activities such as fishing. For example, I was fishing last weekend, just a fun little story, and we hooked on to what we thought were weeds. When we reeled in, it was actually about 3 or 4 meters worth of fishing line with the hook and lure still attached. You could tell it wasn't in the water for very long. We were just lucky that we were able to pull it out and hooked on. But just something to think about, even those fun activities like fishing. I don't know any other activities right now, swimming.
Well, Joni has asked, are they found in any foods in the chat? And I think it's really important to mention that microplastics are nearly ubiquitous, meaning they're found in all foods. Pretty much anything that's ever come in contact with plastic, whether it's in the processing, if you use your plastic cutting board, if it's in a plastic package, they can really come in any which way. So it's important to note that plastics are nearly ubiquitous in our society.
Yeah, and Sherry mentioned a lot of plastic ropes when camping. Exactly, a lot of people leave their ropes and supplies at campsites. Unfortunately, they're done with them and they just let them be, which is very unfortunate. That's part of the leave no trace principle that a lot of people need to follow.
Awesome. And if you have any more questions, feel free to ask in the chat. We will have a Q&A session at the end of the meeting as well. So feel free to shout out then.
Yeah, thank you. So now we know a little bit about what microplastics are, how we categorize them, and where they come from. So I hope everybody has a bit of a good understanding about that now. And then I will pass it over to Ajaz to discuss how we find microplastics and what we use, the tools we use when working with microplastics.
Thank you very much, Carly and Isaac. You were really awesome. So, all right, let's talk about how we actually collect and analyze microplastics. Here, we're using Saturna imaging system, which is developed by Ocean Diagnostics. The question is, why Saturna? I think because traditional microplastic analysis can take hours of stirring into microscope. It's slow, tiring, and sometimes inconsistent, I would say. Saturna makes it faster, easier, and standardized, so communities like ours can collect reliable data without needing a big lab. It also works perfectly with beach quadrant sampling. That's why our results are consistent and comparable across different beaches, communities, and even across the years of sampling. So I would say, in short, quadrant and Saturna, reliable community sense. Now, let's talk about the sampling process, how we actually collect and sample. I'll go just a little step by step. So the first, we place a quadrant, basically square frame on a pre-selected beach zone. That could be high tide line or mid beach or even backshore. Then we scoop 2 centimeters of sand from inside the quadrant. This surface layer is important. Why? It's where the plastic and debris tend to accumulate. Then we pass sense through 1 millimeter sieve to filter our larger materials. And finally, we use a forescope to carefully remove suspected plastics. If needed, we just rinse them to get rid of the sands. And simple steps, I would say, but when done carefully, they make sure every sample is clean, consistent, and ready for analysis. Now comes the exciting part, a Saturna in action. This tool is really portable, a plug and play, I would say, designed for use for both scientists and community members. It uses a background sheet and shroud to make sure every image has same lighting. That might sound small, but it's critical for quality of data. Once the sample is placed, Saturna automatically traces and measures each particles, not just counting them. It provides, I would say, 13 different details like size, shape, color, and circularity. So instead of spending hours under a microscope, Saturna gives us the same, or I would say better results in just minutes. That's why we use it, because it's faster, accurate, and consistent. Yeah. Of course, the real question is what do we do with this information? I would say the Saturna gives us two powerful insights. First, the concentration, how many particles per square meter are in the sand, and the second, the consumption, why these types of plastics we are finding, and in what proportions. So then we can turn those results into sample graphs and visuals. That makes the science easy to share with communities, teachers, and even policymakers. And this is where it all come together. Grassroots sampling plus advanced tool like Saturna means communities have the power to tell a clear story about what's happening in their beaches. And that story can lead to action to protect the Great Lakes. In short, we use Saturna because it makes microplastic monitoring faster, easier, and more reliable. And when we share those results, the data turns into story, and that story drives the actions. Thank you very much.
Awesome. Thank you so much for that, Ajaz. And now I want to give a warm welcome to our special guest speaker, Dr. Roxana. We are so happy to have her here. When we were searching for folks who might want to speak at our webinar here, you were one of the first people that came to mind. Dr. Sühring has done a lot of work on microplastics and their chemical makeup, treating them as a potentially toxic pollutant rather than just a small object, right? What happens to them as they break down chemically? So I'll turn it away to Roxana. Thank you so much for joining us.
Thank you so much for having me and for the introduction. And yeah, awesome for all of that background information as well, because that will really help with this talk. And so what I've called this talk is Plastics, Waste, or Toxic Chemicals, because that is really what we are focusing on in my lab, where we are trying to look at plastics as complex chemical mixtures. And so this is to an extent because I am a chemist. And so obviously I like to think about things as chemicals. But I hope by the end of this talk, I will have convinced you that this is actually what I would argue a way of how we need to look at microplastics as environmental contaminants. So next slide, please. But just to back up a little bit and talk about plastics, we've heard a wonderful introduction here. But really, what I think is important to note is that global plastic pollution is an environmental crisis, right? You might have heard about the planetary boundary concept. If you haven't, don't worry about it. But so basically, the idea behind this is that there are a couple of distinct factors or processes on this earth that basically make sure that we as humans can live here well. This includes, for example, our climate, have a stable climate that includes things like that we need biodiversity, we need to make sure that our oceans are healthy. We need to have access to fresh water. So a variety of these specific, what they call boundaries. And what we're worried about is that these boundaries or that these systems might be destabilized. And so a recent paper that came out is basically they looked at what the impact of plastics is on those different types of boundaries and found that plastics interact with basically every single one of them and oftentimes lead or enhance a potential destabilization. So be that from contributing to climate change, acidifying our oceans, or, for example, messing with our biosphere and integrity. Next slide, please. So we clearly know that plastics as pollutants are an issue, but why does it matter whether they are a waste and a particle or if they are a chemical mixture? And so here I wanted to point you to something that happened now, a bit over a year ago, where Canada actually tried to have plastics or microplastics particularly listed as a toxic substance under federal regulation. So this would enable more easy regulatory response to plastics as a potential contaminant threat. So, but now what happened was that basically this initiative got shut down by a judge because in the dossier that was submitted where we tried to get microplastics listed as a toxic substance, there was a lot of talk about waste. And the judge rightfully so said that waste is the jurisdiction of provinces and municipalities, not of the federal government. So basically what ended up happening was that we weren't able to have plastics listed as potential toxic substances, not because people were saying this isn't actually toxic, this isn't dangerous, but because it's not a federal government issue and toxic substances are regulated federally. So it makes a huge difference. It really binds our hands behind our backs, basically, if we think of plastics just as waste. Next slide, please. So, but then is there a question? Oh, is there actually a toxic potential of plastics, right? Because one might argue, well, if it's just waste, is it really a toxic problem? Because a lot of the stories about larger plastic waste we might see is what is here in this newspaper article, for example, where mismanaged waste is considered a problem, particularly because, there's, for example, viruses or bacteria that can, grow on those. You might even sometimes have rodents use these as rafts to get from one place to another. So it is really a waste problem at that sense, right? So, but what we also see is that plastics, and Carly had given a really nice introduction here, but that we see these microplastics absolutely everywhere around the globe in, for example, tap water. So this figure here just shows you the percentage of tap water worldwide in different areas that are contaminated with plastic fibers. And so if you look at that, so worldwide, it's over 80%, but practically no matter where you go, you will have at least over 70% of tap water contaminated with microfibers. So next slide, please. So, and now, why do we think that these microfibers might be actual toxins rather than just physical objects? Well, so if I, as a chemist, think about a plastic, it looks more like on this slide. Because so a plastic itself is first of all made up of a polymer backbone. And that is these polys that you might see, if you want to look for something that might contain microbeads. So that might be, your polyethylene, or your polypropylene, or your polystyrene, or all of those. That is just the backbone of your plastic. Then what gets added into it is a lot of what we call functional plastic additives that gave any product the properties you want. So this might be the color, right? Most plastics are some sort of beige, gray, or whatever. You might want it to be colorful or sparkly or whatever. So these are colors you need to add. You might want the plastic to be squishy, or you might want it to be really rigid. You might want it to use it outside, then you need to add stuff in like UV stabilizers. You might want to, use it in a very specific application where you might have a specific chemical stress on it. And then again, you add different types of additives to make it resist that. So in the end, what we end up happening is that these plastics that we have as a final product are full of different types of chemicals that can potentially then leach out later on. Next slide, please. So, and now the next question is, and there again, Carly has kind of commented on this already. Well, if plastics were just a waste issue because we've just basically discovered they are a chemical mixture, but if they were just a waste issue, you would expect that they are only released into the environment once you're done using them, right? That's by definition waste. But what we see with plastics is that really, if you have a plastic product, microplastics can be released throughout the life cycle of that product. Be that when it's being made, because while you mold the plastic, like you melt it down and you mold it into different shapes, you have all of these clippings that are getting released. While you use it, you might have release through, for example, laundry, as we talked about earlier, with clothes. But also, for example, if you drive your car, your tires will be shedding particles just by you using the car as intended. And then obviously there is release at the what we call end of life cycle. So where, for example, you might have littering of your food containers or your, like grocery shopping bags, but also just any item that ends up in the landfill, might be released back into the environment. Next slide, please. So, but then do we actually see specific chemical effects from plastics? Because, okay, they contained chemicals, but that doesn't necessarily mean they do anything, right? So, and this is some research that we did in my lab. And so basically, this is going back to the wastewater treatment systems that Carly talked about, where we already talked about that they are not necessarily very good at filtering out the plastics. They weren't designed to do that, but it's quite frankly worse than that. Because what wastewater treatment plants were designed for is to reduce nutrients, particularly nitrogen and phosphate. That's the stuff that causes algae blooms and what we call eutrophication. So what we saw, this is a test we did, where we put a representative amount of microplastics that we typically see in wastewater treatment plants into a wastewater system and looked at how is then the nutrient removal working. And what you can see here is that, for example, removal of phosphate was reduced from about 90% to down to 60 when adding fibers. And total nitrogen was reduced from over 90% removal without fibers to just about 30%. So this means that the plastic particles not only themselves aren't removed properly, but they actually make our wastewater treatment worse, right? So that's obviously a toxic issue. Next slide, please. So then what are we doing about this globally as a society, right? And luckily there is quite a bit of stuff being done. So, there's, for example, microplastics in cosmetics have been banned in a lot of different places. So these microbeads, you might still see them, but they are banned in a lot of places. There's also on this map, for example, you see, this is a map of places where these like flimsy single-use plastic bags have been banned or restricted, or you need to pay for them. to reduce that because they are actually contributing to a lot of microplastics in the environment. One thing that I specifically wanted to point out is also that California, for example, is moving towards introducing limit values to how much microplastics you can have in any given water, or drinking water, where you might have something like, okay, and you have to be below 100 particles per liter or something like that. Next slide, please. So, and that is obviously wonderful that there's something being done about this. But particularly with these limit values, which is really with a lot of chemicals, what enables us to reduce contamination loads is when you have regulatory limits. Well, how do you enforce it with microplastics? Because what we just talked about is that there's lots and lots of different potential sources. There's lots and lots of potential different types of plastics. So, well, if you now have a river and you say, well, you can't have more than 100 microplastics per liter, and then you find 10,000, well, what are you going to do about it, right? Like, whom are you going to fine? Who's going to pay for remediation? How are you going to turn off the tap if this is ongoing contamination? If you don't know where stuff is coming from. And right now, we are very, very bad at that. Next slide, please. So, and this is really where a lot of the research in my lab comes in. We are trying to figure out what are local sources of microplastic contamination so that you can actually do something about managing that as a contaminant, remediating, or potentially also attributing liability. So, and one thing that we found was, and this was with the help of our lovely collaborators in California, and sorry, it's a little cut off here on the side, but basically they did a survey of what type of plastic items they were finding along various California beaches. Oh, back please. Thank you. Over the last 30 years. And the interesting thing is that this was actually quite consistent. So what you can see here is that, so for example, food containers, cutlery, lids, plastic bottles, bags, straws were consistently sort of within the top 10 of plastic items found in the environment over like the last 30 years. So then our question was, well, can't we then use actually this type of information? Because thinking back to different products have different functional additives added to them. So can we use that chemical complexity that is often so baffling as actually a way of tracking what type of product a microplastic came from when we find it in the environment? Next slide, please. Yeah, wonderful. So, no, one back. Wonderful. So now this is a bit of a weird graph, but I'll walk you through it. Because basically what we did was we used, we're chemists, right? So we used lots of analytical chemical information on the different plastic additives of different types of plastics that volunteers as well as regulators collected for us across California particularly. So, and we looked at, so if you analyze a plastic particle or a plastic item like that, you'll find thousands of chemicals in them. So this chemical complexity we used to try and basically statistically see if we can distinguish those different products. And so in this graph, what you see is basically any sort of blob there that is differently colored is a type of plastic. And the further these blobs are away from one another, the more distinct, the more different the chemical patterns of these plastics actually were. So with this, what we could see is actually that, sure, we actually could distinguish things like food wrappers from plastic toys, from Ziploc bags, from cigarette tips, right? So there were a lot of different plastic items that we could actually distinguish based on their chemical fingerprints. So that made us really, confident in trying to automate this. And that's what we did next. So next slide, please. Another crazy looking graph, but basically what we did was we now increased our collaborations. We invited even more people to get us data on these plastic, what we call plastic fingerprints. And what we ended up doing was we fed all of this in a machine learning algorithm, and basically started to classify different plastic microplastics into the types of products. And what we found was that using these different analytical techniques and combinations thereof, we were able to correctly classify all of these different types of products that you're seeing at the top here. So these were ranged from what we call food contact materials, like be that, cutlery, be that plastics, wrappings, food containers, to toys, balloons, toy balls, to, construction material, to, fishing baits. All of these different things we could accurately classify using our method, which then also enabled us to identify other specific types of chemicals that are of particular concern. So, and here, next slide, please. This is just to give you a little bit of an overview of the variety of different types of plastic additives and different chemicals we were finding. So don't worry if all of these structures don't mean anything to you. I just want you to see that they are all looking really different, right? And what we are seeing is that all of them had really different kind of uses within a plastic as well, which is what made them so specific to the type of plastic item. And what you can see here is we have, for example, colorants, we have flame retardants, we have UV stabilizers or biocides. All of those we found in those different plastic items. And what you can also see on here that a lot of them, unfortunately, are known to be toxic. So, for example, their 1,4-dioxane, the very first one, is a carcinogen. So that means it can cause cancer. It is a 1B, which means it is known to cause cancer in humans. We have some that are reproductive toxins. We have others that are neurotoxins, so, work on brain development or can be problematic for that. Or what we call endocrine disruptors, which are chemicals that mess with the hormone system. So really what our approach enabled us to do was to, first of all, find major plastic sources that microplastics were coming from in terms of products, but also identify particularly problematic additives that are being used frequently in those plastic products. Next slide, please. So then really the takeaways here are that plastics are complex mixtures and they are released throughout the life cycle of plastics. So this means they aren't just a waste problem. They are complex chemical mixtures and should really be labeled as toxic chemicals regulated under the federal legislation. The chemical mixtures, though, that make up those plastics and are so complicated are actually the thing that can really help us identify where these plastics are coming from. And in order to identify, for example, local sources, to address microplastic pollutions, we really need to get this variety of information, be that on the physical object, very much like was now presented what you at NORDIK are doing, together with this type of chemical information that we are doing in a chemistry lab. So we really need to break up those silos. We really need to work together. And so for that, I am so excited to have initiatives like this, to have communities involved. We couldn't have done any of this without the fabulous volunteers who got us these samples. Yeah. And with that, I would like to thank you. And I think on the last slide, I have a couple of our funders as well and collaborators who have contributed to this project and my wonderful team. Thank you very much.
Thank you, Roxana. That was great. Very, very interesting, very informative. Yeah, that's awesome. We really appreciate you being here and giving this talk. Before we move on, there were a few questions in the chat during your presentation I'd like to go back and touch on before finishing up our webinar. Elaine, thank you for answering some of the questions. Really appreciate it. But if it's okay with you, Roxana, I was thinking Isaac and I would just go through and read them off so we don't miss any, and then you can answer.
Yeah, great.
Okay, awesome. So Isaac, if you want to
Sure.
go to the top.
I'm just going to move to the next. Oops, sorry. Yeah, so thanks so much. It's tricky to tell which questions are for who. Vitriac, Vitrique, it's Kiki. Okay, sorry about that. Is this data open to the public?
So I think I saw that question coming in, and I think that was particularly about the 30 years of sampling. I am not sure whether that has been published as of yet, that data just itself. We are, right as we speak, basically, I'm writing a publication where this data is going to be included. So, hang on tight. We're submitting it hopefully very soon. But also, if you're interested, I'm very happy to put you in contact with the people at the California Water Agency who actually are basically in charge of collecting this.
Awesome, thank you. And we have a question from Ron. Can the federal government work with provincial and municipal governments to list toxic substances? If it isn't our safety and that of our environment more important than a silly jurisdictional battle?
I agree. I very much agree. So, and this is really, this is the thing, right? Like, so very much the wording here was the issue, because so when you talk about waste, it's about waste management. Whereas toxic substances very much are regulated federally. And I agree that there should be more working together. But obviously, provinces are very hesitant to give up any of their jurisdictional power to the federal government. I would argue, though, that the whole point in case of plastics is moot, because it is indeed a chemical and a toxic substance problem. So very much this is now going through additional steps where hopefully this will eventually be happening, that we can list these chemicals. But what is so interesting with this is that sometimes just the wording is gonna, push back progress like this for years. Because obviously you will always have the lobbying on the other side, basically, who will, be fighting tooth and claw to try and keep federal regulation of plastics.
Right. Okay, thank you. I think that's all the questions I see that were not answered. Do you see any?
No, I think that was it. Thank you so much.
Okay, great. Yes, thank you. Okay. Okay, so to close today, we just want to touch on what you can do as community members, volunteers, members of our society. So first of all, educate yourself on how to prevent microplastics from entering the Great Lakes, which everybody here is doing today just by attending this webinar. So thank you all for attending once again. And of course, share what you learned today, whether that's with family, friends, you're just outside and you see some litter on the ground, or you see somebody litter. Yeah, Joni, you have a question?
We have a very specific issue here in the Lake Superior watershed north of Sault Ste. Marie, and it involves a wastewater treatment plant. And I was just bringing it because there's probably a lot of people here who are aware of it. But this whole incredible program that you've given today, this incredible knowledge, seems like a real additive to the discussion around what is potentially unfolding with this business, with this wastewater treatment plant into a major river of Lake Superior, which is the Goulet River. Anyway, I just wanted to raise that because I don't know how all of this knowledge fits in, but there's a group of people here on this Zoom, and I wanted to bring it up if Nordic isn't fully aware of it, that would be really great to have a further discussion.
Yeah, so thank you so much. I mean, we are always happy to learn more and to chat about community concerns. That's really why we're here, right? Is to bring community concerns into a format that they can be brought before lawmakers and organizations and stakeholders. So yeah, we would definitely love to get in touch. We are aware a little bit of the situation that you speak of, but we're happy to learn more and chat with you folks if you would like to send us an email.
Yeah, Kiki, our Lake Superior coordinator, just commented in the chat. She's aware and is definitely interested in chatting. So, so good to know, and thanks for bringing that up, Joni.
I'm putting Kiki's email address in the chat so you can reach out to her if you want to set up a time. Thanks.
That would be wonderful. And Roxana, do you have any Indigenous chemists just bringing that Indigenous lens to the work that you do?
Yes, thank you so much for the question. Yes, so I am really, really privileged to work with Indigenous communities, particularly I'm working quite closely with Nipissing First Nation, as well as the Nunatsiavut government up in Nunavut. And in my lab, I do have Indigenous students from a variety of different communities, mostly Mohawk from Six Nations, Cree from Moose Factory, and yeah. And yeah, I think this is so important, like particularly because a lot of, when talking about, for example, justice questions around contamination, very often when we look at First Nation or Indigenous communities in general, they are more impacted. And there's often less resilience as well to these type of contamination issues. And so I think it is incredibly important to work with the communities and really co-create with communities and have researchers from those communities work on these types of questions.
Thank you so much. That really speaks to the strategy that Nordic has to work with rural and remote communities, which are largely Indigenous.
Yes.
So thank you very, very much for your work today and sharing this.
Thank you.
And Kiki, go ahead.
Hi, I'm going to jump in. Hi, Roxana. Thank you, everybody. Roxana, I have a question. For future presentations, now that Joni's brought some things up, would you be interested? I also work with the team at Nordic. Would you be interested in possibly doing other presentations for some other northern communities that possibly weren't able to come today, or possibly recording something for us? Because I too find this very valuable, especially when it comes to wastewater, and especially because we're at the top of the food chain here. So everything that we have is going down, right? So it gives us a little bit more of a responsibility, I feel.
Yes, no, absolutely. Very happy to. There's also particularly, so some of the work that I now obviously could talk about in the interest of time, but we do a lot of work in the Arctic as well with staple foods, particularly. So be that fish and seabirds and plastic associated contaminants there. So very happy to, to keep chatting and yeah.
Wonderful. Thank you. I'll definitely be reaching out.
Awesome.
Okay, awesome. Thank you. Well, we are running out of time. So if anybody has any last questions, feel free to raise your hand or type them in the chat. I did just add a link in the chat, and that is to the Nordic Water Team volunteer sign-up form, as Isaac just mentioned. So if you're interested in volunteering with us and becoming a water monitor, please fill out the form and we can be in touch. If there's no further questions, I want to thank everybody for joining. Thank you for your time today. Thank you, Roxana, for your time and your wonderful presentation. And we will be in touch with a follow-up email. But other than that, thank you everybody for being here today. I don't think there's any further questions. So this is great. Thank you all.
Awesome. We would love it if you want to stay in touch with us, again, to go through the link, as well as to find us on social media. And also follow Roxana's wonderful social medias and conferences and research as well. The TMU website has a list of Roxana's publications and research as well, so feel free to check it out. Thank you all so much for coming.
Thank you so much. And as a scientist, I'm always happy to talk about my work, so please feel free to reach out.